Hello everyone. In this video, we will introduce three algorithms for Splendor, the BFS, A-star, and approximate Q-learning. Also, we will talk about applications, challenges, and ways to improve them. The first method is BFS, a type of blind search algorithm. Searching in this game works in the same way as the diagram on the left, with each branch representing an action, and each node being a game state. After each action, the game state is changed, and we have no way to get the action of opponent. So when designing this algorithm, before finding the goals, only ourselves doing the action during the search. The biggest challenge we face in this algorithm is the efficiency of the search. This has a stronger relationship with how goals are set. The win condition for this game is to get 15 points, but the goal is too far away for the BFS. So we split this goal into two subgoals, buy cards and get points. This will significantly reduce the number of timeouts. Also, another way to prevent timeouts is pruning. We filter out all low-value actions, such as taking only one gem at a time. Next, I will show how the BFS algorithm performing in the game. As you can see from the results, BFS has no strategy and buy a lot of green cards. You can see the green cards do not help us to buy the high-value cards or get the noble card. Even these three nobles do not need green card. Therefore, we have designed a second algorithm, A-star, with a heuristic function that leads the algorithm to select actions according to our strategy.
The core of A-star algorithm lies in the design of heuristic function. In each round, we first assign weights to different states. Then we use the weight to calculate the h-value of each action. After that, we choose the action with the lowest h-value, and it is regarded as the best action. We also have a timeout protection method. The core strategy of our A-star algorithm is based on the number of noble cards. As the number of noble cards goes down, we need to decrease the weight of noble cards and increase the weight of high-score cards. We also have some challenges. We need to consider the possible situation and manually adjust the parameter of weight. The strategy of heuristic function is fixed. It is not as flexible as the approximate Q-learning algorithm, and although we try to add some function to predict the opposition actions, the actual result is not good. In the future, we will first filter out the useless and meaningless action, such as the action of taking only one gem in every round and taking too many cards of the same color. Then we will set up different detailed strategies for different situations, and we need to consider some more appropriate offense and defense strategies in the future. And we can see the result compared with BFS algorithm. A-star algorithm is much better. Then we can see the demo. Although A-star algorithm wins many times, sometimes it will keep exceeding the limit of gems for many rounds. In this round of game, we can see A-star algorithm get more points in the beginning, but when it keeps exceeding the limit, the BFLS algorithm started getting a lot of points with the noble cards. So we still need to optimize this situation in the future.
Third algorithm we tried is approximate Q-learning. Two main motivations are, firstly, compared to the blind search and heuristic search, approximate Q-learning can involve more and complex strategies designs and would not easily incur timeout problem when it's already been trained. Secondly, during the training stage, agent could learn the correct decision weight vector from the game by itself. The advantages are, this provides a more generalized way to make decisions under similar state situations, as the features would be similar. Due to the approximation, it can help to reduce the size of the Q table which is need to be stored. A logic algorithm is shown here, which is similar to Q-learning, except approximation Q1 calculated by using the linear combination of features. Using the algorithm can be concluded in 3 points. The first, the learning rate count factor need to be set carefully, otherwise it make troubles to let the agent learn the weight vector. The second one is, the performance relies on rival's performance and strategy. If the rival is too hard to beat, or if the rival is too naive, it can hardly learn something through the game. And the fact of limited amount of rivals for training also cannot further improve the performance. The third one is the timing to terminate the training. As different kinds of rivals may have different weight vector to counter, it's difficult to decide which state of the weight vector is the most suitable one. For the future improvement, it could be scaling the features by applying more feature engineering and selection techniques. And the second one is using more rival agent to train the model. The card approximate function is a linear combination of features. It couldn't handle the nonlinear task, so it could be improved by using neural network techniques. The demo would be using approximate Q-learning to play against with breadth search algorithm and A-star algorithm. Firstly, I'll show 10 games of approximate Q-learning versus BFS algorithm. Agent 0 would be approximate Q and agent 1 would be BFS. Result, we can clearly observe that The Ruby, which is the approximate Q-learning, has absolute advantage compared to the C-tree, which is the ABFS. The approximate Q has absolute 100% winning rate and have strong scoring ability. And next, we will go through the 10 games of approximate Q-learning versus A-star algorithm. See that of 10 games, approximate Q-learning has a relatively higher winning rate and a relatively strong ability, but the advantage is not significant as previous one versus BFS. So that's all for the table, and thank you for watching.